chapter 9, our big goal is to solve equations. We will want to solve things like cosine squared theta plus 5 sine theta plus 6 equals 0. And that is a reasonably hard equation to solve. The job will be to get theta by itself. And we will be able to do that as we get really good at identities. You need identities to make the hard equation easy. Now, right now it's hard, but with identities, we can make it easier. And that happened to you in algebra too. In beginning algebra, this equation, 3 times 2x plus 1 plus 5x equals 6. In beginning algebra, this equation is impossible to get x by itself. You cannot solve it, not unless you know an identity. You have to know this identity, and everybody knows that. That's the distributive law, and you've learned that. But before you learn it, that purple equation is impossible. You can't solve for x if you don't know that identity. And this identity allows us to take this hard equation and make it easy. So we get 11x plus 3 equals 6, and we can keep solving now. But it all depended on this identity. If we did not know this, if we didn't know this identity, we would be stuck. And that same thing is going to happen in trigonometry. You're going to learn a bunch of identities, and you're going to use them to become unstuck. The hard equation, you will make it simpler because you know identities. So I want to encourage you, keep memorizing those identity formulas. So we'll just kind of warm up with those basic ones. But then I have a couple new ones for you today. And chapter 9 is going to have new identities all the way through the chapter. So there will be several more formulas to memorize. And we're going to practice. We're going to practice using the trig identities to simplify. How do we make a hard thing simpler? So that we'll be ready. When we're good at that, then we'll be ready for this hard equation. Okay, so that's the basic game plan. We'll look at the new identities, refresh. We'll look at the old identities, and refresh those. We'll look and learn a couple new ones, and then we'll practice using the new ones to simplify things. So here we go. Here is the old identities. Now, we didn't emphasize these last two very much, but you should memorize those now. I'm hoping that now you have the first 6 of them mastered. So add in those last 2 identities because they are going to be valuable. Now, question number 1 and question number 2 is just practice changing. How do you change a hard thing into a simpler thing? We can change it by using identities. Now, in the future, it won't be an expression. In the future, it'll be an equation. And we have to get theta by itself. And we can't solve that equation right now because cotangent theta times sine theta is pretty complicated. We want to make it simpler. Okay, so we're not going to worry about the equations yet. We're just going to concentrate on the expression and say, what can I do to change that expression and make it simpler? What can I do to make it simpler? Well, we're going to learn a few strategies that are pretty common to make a complicated thing better. Sine and cosine is the best trig functions. They're the most comfortable. They're our most user-friendly trig functions. So whenever we have an expression that has tangent, cotangent, secant, cosecant, those are not the user-friendly functions. So it would be nice to swap them out with something better. So I see cotangent right here, and I'm thinking, how can I make that easier? Do you see an identity that we could change the cotangent out with something better? You guys notice any identities there on the left?
1 over tangent.
Exactly, that's a good choice. Anything, do we have any other options?
Cosine over sine.
Yes. So actually cotangent has two possibilities. Now remember, we're thinking about they're both legitimate, they're both correct, and they both would make a change to that hard problem. But then you also have to ask yourself, which one is going to change it to be the nicest? If I do 1 over tangent times sine, I don't think that's really making it. It's true, by the way. That is a correct, a true transformation. We changed it into something different. But our secondary question is, okay, yes, that's a correct change, but is it simpler? Is it better? And I'm thinking, well, it's actually kind of worse because now I've got a fraction and I still have tangent. Tangent's not the nicest one. So since we had 2 to choose from, I'm not liking that one as much. I'm liking this one better. So I'm going to take the cotangent out and change it into cosine theta over sine theta. Now, I like this one a lot more because the hard expression that I started with, I changed it so that everything in there is sine and cosine. So this is going to be a guiding principle for you on pretty much everything in chapter 9. If you have a hard statement, it's good to change it into only sines and cosines. So try to figure out a way to swap out all the hard stuff into sines and cosines. And we did that. Okay, so we did that with an identity. Now, can we simplify it more?
You can cross cancel the sign.
Okay, be careful. If you have proportions, we call this cross multiply. And so some people get mixed up and confuse cross canceling with cross multiplying. Cross canceling is a little bit of a weird word. I suggest you just think about it as a divide problem. You divide on the top and divide on the bottom. So I'm going to make this a fraction by putting a 1 under it. And so it's not so much a cross because you don't have to have fractions. Here is 8 over 14 times 6 over 5. Okay, it doesn't, when you're dividing, you don't have to divide across. You just divide the top and divide the bottom, because I can divide by 2 and I can divide by 2. And that's not a cross. You're dividing the top and the bottom. So when you're thinking about fractions, just think about dividing top and bottom. And on this one, this is kind of what Caleb was hinting at, though. You can divide the top, cancel sine. Divide the bottom, sine divided by sine, divides out the sine. They cancel each other out. So sine divided by sine is 1. And after we do that fraction reducing, we get a really simple answer. So we started with something that was hard, and now it's very simple. That's the game plan that we're working towards in chapter 9, is using identities to get from a hard thing to an easy thing. Okay, let's do the same thing on the question number 2. Cosecant, that's not one of the easy functions. I don't want to say it out loud, and I don't want you to say it out loud. I want you to write down, how can we change both of these and make them easier? So on your paper, take a minute and you write it down right now. What can be an easier transformation of that statement into something simpler? I'll give you a minute to write it in your paper yourself. Okay, what did you guys find to change the cosecant?
1 over sine.
Yep, there's really only one choice, and I like that choice because I like sine better than cosecant. So now my expression has sines in it. It doesn't have the complicated cosecant in it. Okay, somebody else, what did you find to do for tangent?
Sine over cosine.
Yes, that I like as well. It is right over here. Now, technically, if we wanted to, tangent equals 1 over cotangent. So theoretically, I could have plugged that in here. It would have been true, but not helpful, because then I would have switched the problem into having cotangent instead of tangent, and it would have been true, but not as helpful. This purple one that you guys came up with is the best plan because the only things in the expression now are sines and cosines. Those are our most user-friendly expressions, and now we can do a little bit of algebra and clean this up. And it's going to be very much like the last problem. A sine divided by sine is 1. I'm canceling. Canceling is a nickname for dividing. Sine divided by sine equals 1. And what's left? Equals 1 over cosine. So we took that hard statement and made it simpler. Now, for some people, that's good enough, and you're done. But 1 over cosine does become secant theta. So either one of these would be okay. Kind of depends on the context of the problem. But as far as equations go, this one's best for equations. And that'll be later in the chapter. Okay, so that's a beginning warm-up of simplifying with identities. So I think we've actually even worked this some. But now I want to introduce you to some new identities. The new identities have fancy names. They're called even and odd. And briefly, back in chapter 3, we talked about even and odd functions. And there's a whole technical theory behind what even functions do and what odd functions do. Now, that technical theory is not that critical for us in trigonometry. But what you should know is these two here. So these you want to memorize. Sine of negative theta equals negative sine theta. And cosine of negative theta equals cosine of theta. Real briefly, here's some logic to that. And I have a theta. This point is the point cosine theta sine theta. Now, we learned that a long time ago. It's the definition of the unit circle. Now, imagine theta is not positive, but it is negative. So the blue one is negative theta, and it puts me exactly symmetrical to it below on the quadrant 4. So this point will be cosine negative theta sine of negative theta. That's the unit circle definition. Now the blue one makes a triangle, and that is the negative theta. The black one makes a triangle. That's the positive theta. And I didn't draw my picture very well, but the blue and black triangles are exactly the same, except one is standing up and one is standing upside down. They're exactly the same. So this distance right here is x. So when I go on top, this is x. But when I go on the bottom, it is also x. Because quadrant 1, x is positive. And in quadrant 4, x is positive. These have to be the same. So it's kind of a quick visual argument that cosine of theta equals cosine of negative theta. So it's just a little quick proof about that. You plug a negative angle into cosine, it's the same as the cosine in the positive angle. Now, the y numbers, this one is up. And this one is down. So this y is positive and this y is negative. But the numbers are the same. So one is in the first quadrant, I have to go up for the sign. And in the second quadrant, in quadrant 4, I have to go down for the sign. But in either case, I'm going to go up 0.8 or down 0.8. So that means these two are opposites. If I do the blue one, it is not the same as sine theta. They're not the same. They are opposites. So one is positive and one is negative, and I'm just going to put the negative right here. And so that way it tells, oh, I've got the opposite. Now, for some of you, that kind of clicks in and intuitively you can kind of see it. And that's all that I want you to get right now, is just the intuition there. If you did not get that intuition, it's okay. You still have to learn these and get really good at them. Okay, so number 3, I want to simplify this. Now, it's not simple because one of them has a negative theta inside, and I also have a tangent of theta on this problem. So I want to start simplifying that number 3. So this is not so nice. How can I make that better? What is cosine of negative theta equal to? Well, this is our new identity. Cosine of negative theta equals what?
Cosine theta.
Exactly. So that problem is now simpler because both of them have positive angles now. I went from one negative angle and one positive angle to at least both of them are positive angles. And we can do other identities from the simpler ones that we remember, like sine theta over cosine theta. That's tangent. And I can make a fraction out of both of them, put a 1 under cosine, and cosine divided by cosine cancels to 1. So in the end, that hard statement simplifies to a very simple thing, sine alone. Now, the purple box, that's really the only one you have to memorize. Because, you know, if you don't have to memorize secant, because you can change secant into 1 over cosine. I've made this problem a multiple choice question because I think Newton has some multiple choice questions. But typically, what are you going to have to do? Well, you're just going to have to simplify it piece by piece. So if I were to simplify this piece by piece, I would start getting rid of this. Cotangent, that's not one of my favorite functions. It's more complicated. So I prefer having a trig function for that. A sine cosine equation. What is cotangent?
Cosine over sine.
Right. Secant. I prefer coming up with a more user-friendly version of secant. And that one is 1 over what?
Cosine.
Yeah, except it's cosine of negative theta. It was secant negative theta, so I'm using the secant and flipping the secant into 1 over cosine. Okay, so I made that hard problem a lot easier because now it is only sines and cosines. But some of them are negative thetas and some of them are positive thetas. So we could simplify that a little bit. Let's simplify this one. What is sine and negative theta?
Negative sine theta.
Exactly. And then cosine of theta, sine theta is still the same. And then lastly, what is cosine of negative theta? That's cosine of positive theta. Does anything cancel? Does anything divide and reduce here? Yes, everything divides. I divide cosine on the top and divide cosine on the bottom. And each time I divide cosine, I get cosine divided by cosine is 1 on the top. Cosine divided by cosine on the bottom is also a 1. The first one's not a fraction, so I'll put a 1 under it. Now it is a fraction. And sine divided by sine gives me 1. Multiply everything that's left. What's left? What does that equal?
Minus
Negative
1.
1.
It does. I have 1 times 1 times 1 on the top, 1 times 1 times 1 on the bottom. 1 divided by 1 is 1 times that negative. That's the negative 1. So that giant hard problem in number 4 actually simplified to a very simple thing. It equals negative 1. Okay, a couple more identities. These identities here in the box, I want you to memorize. So sines and cosine, anything to do with sine and cosine, memorize the new identity. It has to do with the shifts. If you look at a sine wave carefully and you shift it back a little bit, you'll see the cosine falls right back on top of the sine wave and vice versa. If you shift the sine wave back, it falls right on top of the cosine. The two waves are off of each other by a 90-degree phase shift. So these two equations are kind of capturing that principle that a sine is equal to a cosine of 90 minus theta. They're off by that 90-degree shift. Now, we can use that sometimes. By the way, these are called co-functions because this is cosine. And tangent, this is cotangent. So the tangent and its co-function are shifted off by 90 degrees. Same with secant and cosecant. The secant and the cosecant are off of each other by 90 degrees. Now that's also the same as pi halves if we're doing in radians. Now, if I want to find the exact answer, no, I can't always find the exact answer. What I want to do is forget that, I'm off track. I want to change cosine of 75 into its co-function. Well, what's the partner to cosine? It is sine. So I'm going to make a sine problem here. Well, that equals sine of what?
$75.
We're going to use the 75, that's the theta, but we're going to plug it in down here. So it's going to be 90 minus the 75. That is the co-function. And if I simplify 90 minus 75, it's the sine of 15 degrees. Those two problems have the same answer. Notice they're off by 90. 75 plus 15 makes 90, so they're out of phase by 90 degrees. If I want to switch the sign of pi 12ths into a cosine, question mark of what? Well, I'm going to have to use the cofunction. The cofunction for sine is cosine, so I'm going to have to plug it into, oops, not that one. I need radians, that one. So I'm going to take the pi halves minus this one here, pi 12ths. Now, you cannot do pi fractions in your calculator. If you're bad at fractions, you can do 1/2 minus 1/12. Convert that to fraction in the calculator. You're going to have to figure out how to get good at those. And then you multiply the answer by pi afterwards. But if you just say, well, just live with it, I need a common denominator times by 6. So this will equal 6 pi over 12 minus 1 pi over 12, which equals cosine of 5 pi 12ths. That is switching the sine function into its cosine function. These are called co-functions.